Okay, I think we should start. As you saw, we are live streaming this session on YouTube also, so that maybe more people, also the ones who are not here, can basically have a look at the presentations if they want. Yeah, welcome again to this second part of the FMBC 2020 workshop, which has 3 sessions today. So Merkle trees, consensus protocols, and then at the end lightning talks. And after each session, we will have a short breakout session so that people can also have the opportunity to meet and chat with each other. Yeah, I think we should start now. Our first speaker is Andreas Lochbieler, who is going to talk about authenticated data structures as functors in Isabelle. Andreas, I see you managed to set up everything. Perfect.
Hopefully.
So,
yeah, so thanks for the introduction, Diego. This talk is about authenticated data structures from a functorial perspective and how we formalize them in Isabelle Hall. It's joint work with Ogni and Marriage. We work together at Digital Asset on the open source smart contract language DAML and the ledger synchronization protocol Canton. So this is about distributed ledgers and authenticated data structures abundant those, but what are they actually? Well, in our view, the main business value of a distributed ledger is that they provide an abstraction of a shared database to multiple organizations. Now, compared to traditional distributed databases, the main difference is the trust assumption, namely that the trust boundaries run right through the database. That gives the organization the opportunity to write applications that act uniformly, be that data that is only relevant for that organization and should be confidential, like internal calculations, accounts, planning, and so on. And data that is shared with other organizations, like contracts, obligations, and the like. And in that view, a smart contract essentially defines the data schema for the database, and its algorithm correspond to stored procedures that govern how that data may evolve. Now, this is a nice abstraction. The implementation obviously looks slightly different. Every organization keeps a database on their own. And then there is a synchronization protocol that keeps those databases in sync. And historically, the most well-known and first protocol for such synchronization is you just use a blockchain. You put all the data on that blockchain, and then every organization can process the blocks in order and verify that everything is right. Now, this has a number of problems. One is scalability. If you have every organization process every update to the database, then organization 3 will also be involved in a workflow only between those 2 organizations, and we just end up with scalability problems. Similarly, if you put the data directly on the blockchain, then of course it's very hard for organization 1 to keep parts of their data confidential. And since blockchains are immutable, it's also hard to remove that data if there are regulatory requirements like GDPR or HIPAA that require you to do so. And that's why we started to develop Canton, which doesn't need a blockchain, but provides similar trust guarantees and a setup using an atomic commit protocol rather than a blockchain. But for this talk, we can focus on the underlying data structures that actually ensure that we can have these trust boundaries running through the database in the abstract sense, namely authenticated data structures. So what is an authenticated data structure? Well, technically, conceptually, it's just data arranged in some sort of tree. And the prototypical example would be a Merkle tree, as we see here on the right, where we store data in the leaves and we have inner binary nodes. But we could also think of a blockchain, as a degenerate form of tree, namely a list, or something vastly more complicated like the transaction trees that we have in Canton. Here we see one example of a purchase agreement being executed with its two legs, where one leg moves the money and the other leg moves the virtualized good. Now, that's just data structures. What makes this authenticated is that each such authenticated data structure has a notion of a digest, which acts as a unique reference to the data structure that's being referred to. And people can thus talk about the data structure without knowing its contents. And that's complemented by an inclusion proof, or sometimes also called a Merkle proof in the context of a Merkle tree, that allows you to prove to someone that says, oh, well, here's the digest. And by the way, the data structure that this digest refers to contains at a particular position, a particular value, just like this number 2. And in order to reason about such data structures, as part of reasoning about distributed ledgers, we started to look into how do we actually formalize these concepts and work that out. And the contributions in the paper is basically a shallow embedding of data structures, authenticated data structures into whole. We've implemented that in Isabelle, but you could apply that to basically every interactive proof assistant that can express something like a higher order functional language and data types. Now, this is very systematic, and we start with very small building blocks and then compose them into a complicated, large construction, so we can reach things like Canton trees without having our proofs explode. And we applied the theory to formalize the Canton trees and a few other things. There's one caveat: we're working in the symbolic cryptography model. That is, we're assuming that cryptography is perfect. In our case, this boils down to the assumption that there are no hash collisions. But in the future, we would like to relax this assumption and also be able to reason about hash collisions. Now, to demonstrate what modular construction means, we'll look at the Merkle trees in a tiny bit, but it works the same way for all the other things. So, a binary tree, we can define that as a data type that either consists of a leaf that contains data, or it corresponds to an inner node which has as contents the two children, right? And then we also need to specify where we want to compute hashes. And this is done by marking this with a blindable type constructor, which at this level is just the identity. It serves just as a syntactic marker that here is a place where we want to compute a hash. And these hashes will then be used to form the digests. Now, once we have that, and it works for all data types as you will, similarly, the rest is more or less a syntactic transformation. So we can define a type of symbolic digests by just taking this declaration up here and replacing every type constructor that appears there by its counterpart, the version with a hash, and we use the subscript h. And here, blindable age is no longer the identity constructor. And we can do the same for inclusion proofs, or the Merkle proofs. They're a bit more complicated because inclusion proofs contain both the data and hashes, therefore they have two type variables, but otherwise the construction is the same. And this not only applies to the type definitions, we also get operations. Hash, for example, computes the digest that corresponds to an inclusion proof, and this is phrased as a transformation function that takes such a hash function on the atoms that are stored in the tree and lifts that to a hash function on trees. And this lifting is where the functorial view comes into play. Now, rather than understanding this definition in full, what I want you to see is that this is just as systematic as we had defined the data types. So every type up here corresponds to a particular function down here. And we can compose them just using function application. And the data type is represented by the recursion here. Now, this not only works for the hash function, we also have another operation on inclusion proofs for merging that. And of course, a number of operations. Also, we want to reason about them. So we want to have properties. And these properties are specified by a predicate that we call Merkle interface. Now, the key
there's
point
just
here
one question. We actually, the live talks are a bit shorter than the full talk.
I know, this is my last slide.
Ah, okay. Ah, perfect. Okay, then go on.
Yeah. Yep. So the Merkle interface, what we do is we prove such preservation theorems. And we prove these preservation theorems again from very small building blocks. So we prove similar limits for the plus, for the product, for blindables, and for fixed points, and then we just compose everything. And that's how the modularity is achieved, and how we can scale it to something like Canton, where we have 12 compositions and 2 fixed points. If you want to find more about it, read the paper, look at the series on the archive of formal proofs. They're freely available. Talk to us, or visit daml.com or canton.io if you're more interested in the smart contract language and the protocol. Thank you.
Thank you, Andreas, for sticking to the time, more or less. We had already a question on Slack, which you perfectly answered beforehand to save the time from the QAs. So we can now go ahead to the next presentation. Thank you very much for your nice work and your contribution to the workshop. So our next speaker today is Ante Derek, which will present their work on a mechanized formal model of the Bitcoin's blockchain validation procedures.
Hello, everyone. I hope you can hear me and you can see my screen. So my name is Ante Derek. I'll be talking about our work on building a mechanized formal model for Bitcoin's blockchain validation procedures. And this is joint work with Christian Rupic and Lovro Rožić. Not much of an introduction is needed at this venue. We are all aware that Bitcoin is a great target for formal verification. It is mission critical. It stores billions of dollars in value. And despite being relatively mature, it still suffers from design flaws and implementation bugs. Some are just inconvenient and some can be catastrophic. Also, the development practices are not really what you expect from such a critical system. Important changes are made without unit tests, let alone some sort of formal reasoning. And finally, Bitcoin is often updated with new features and functionalities, and those need to be scrutinized as well. There has been lots of efforts to formally analyze various aspects of the Bitcoin system. However, most of these seem to be focused either on the distributed consensus aspect or on the smart contracts. And in comparison, the basic data structures of the Bitcoin systems, transactions, blocks, blockchains, have received much less attention from our community. And to the best of our knowledge, there were no attempts for computer-aided verification of these aspects of the system. So this is the gap that we aim to fill, and we claim the following contributions. We propose first a fully mechanized formal model of Bitcoin's basic data structures, transactions, blocks, blockchains, including the associated validation logic. We showed the utility of our model by providing machine verifiable proofs for known desired properties of valid blockchain. We mechanize the model and the proofs using the Coq proof assistant. And finally, I want to add that beside the mechanization aspect, our model has some nice additional features in comparison to previous pen and paper state of the art, as we discuss in the paper. A little bit of details. We model the basic data structures as inductive types. We have transaction stubs that contains input, outputs, and other fields. We have transactions that are just pairs of transaction stubs and witnesses, and then blockchains. Blocks are lists of transaction stubs along with witnesses and some other data, and then blockchains are simply linked lists of blocks. Now, if you're paying attention, you can already see several features of our model. For example, we've done away with hash functions completely. For us, hashing is just an identity. So in general, we use symbolic cryptography. You can also see that we only support segregated witness transactions. We do not support legacy transactions. Besides these basic, let's say, outward-facing data structures, under the hood, we heavily use this auxiliary data structure called the transaction history. And the idea is that the transaction history is going to contain a list of all the transactions that are ever added to the blockchain in the order they were added. And now, when we have all of those structures in place, we add validation logic on top of them as first-order inductive predicates. And this is just a glimpse of what that looks like. It's a part of a definition of validity of adding a new transaction to an already valid transaction history. And then in turn, we define validity of blockchains through the validity of transaction history. And then with those definitions in place, after 2,500 lines of code and a moderate amount of sweat and tears by my colleagues, Christian and Lovro, we are able to provide machine verified proofs for the following properties. In a valid blockchain, no coin is spent twice. In a valid blockchain, transactions are unique. And finally, in a valid blockchain, total value of all unspent coins is equal to the sum of all block rewards. And needless to say, I'm being very formal here. All of these results need to be stated very carefully, and indeed they are in the paper. So in conclusion, we provide first a mechanized formal model of basic data structures of the Bitcoin system, and we use it to give machine verifiable proofs of known desired properties. Our model is still a very simplified representation of the real client, of course, and has a number of other limitations that we discuss in the paper. In future work, we mostly want to bring the model closer to the real thing, and we consider soft forks to be the most serious obstacle here. New features are often hacked into the client in a backwards compatible way, and that results in an implementation and a specification that is hard to formalize nicely. Thank you for your attention, and I'm happy to take your questions.
Yeah, thanks a lot, Ante, for your talk. There seems to be no open questions on Slack.
Excellent.
Maybe there is some questions here. Can someone raise their hand?
Okay, so James C has posted one question, but let me try to see it. Okay. Okay, excellent question. So the question is, can I comment on coin-based transactions in Bitcoin which had identical transaction identifiers, and how could that be captured in our model? So this is an excellent question, and problems are these is exactly what we use as motivation. So if you don't know the full story, in the original Bitcoin specification, it was possible to create two transactions that were same when serialized byte by byte, and consequently had two same transaction identifiers, because transaction identifiers are just hashes of serialized transactions. And originally, coin-based transactions only contained the output being created, so essentially the value and the miner address and arbitrary metadata that was chosen by the miner. So what happened in 2010, I believe, that one miner added two coin-based transactions to two different blocks that were exactly the same and had exactly the same hash, and consequently this was very undesirable, and the miner was 50 Bitcoins out of luck, I guess. And what we do in our model, we implement the fixed version. So the Bitcoin standard was subsequently updated to say that you have to explicitly put the height of the block inside the Coinbase transaction. We do exactly that. And with that change, we are able to prove the absence of exactly that bug that you mentioned. So thank you very much for the question, James. This was exactly the kinds of issues that we're trying to verify absence of.
Okay, thanks for the answer. Is there any other questions? Otherwise, I've got one small question. So you kind of, or how did you handle consensus mechanisms in your formalism?
Another excellent question. The short answer is we don't. So we view consensus aspect to be orthogonal to what we're trying to do. There's interesting related work in this field, for example, by Pirle and Sergey, who have a system called Toy Chain, where they model consensus and prove properties of consensus, assuming some properties of the block validation logic. And what we are trying to do is exactly orthogonal. We are discussing block validation logic and are not interested in consensus at all at this point. So basically the property that we show is if I'm a node and if I have performed certain validation procedures, then the blockchain that I have in my memory has certain properties. And we are unable in our model to say anything about other node states and their view of the world.
Are you planning to integrate something for consensus, or do you say no? We don't. So we assume this is another problem, so we stay on.
I think the most desirable thing for me would be following: to take something like a toy chain, which abstracts away block validation logic, and merge it with our block validation logic, and to say that the complete system now captures both the consensus and the block validation logic. I think such approach is needed in order to handle exploding complexity.
Okay, yeah, nice talk. Thank you a lot,
Thank you very much for your question. And if anyone wants to discuss these results, I'm available, and my co-authors are available as well. Thank you.
Yeah, thank you. And yeah, I see the next speaker already started to share his screen.
Bruno, can you hear me?
Kai Brünner is going to speak. Can you hear me, Kai?
I can hear you. Can you hear me?
We can hear you, or at least I can hear you well.
Okay.
And you are going now to present your joint work on towards verifying the Bitcoin S library.
Yes, actually, I have another question for Ante, if I may. Is the time tight? Then we go in the breakout session.
Time is quite tight. Maybe you can post it on
Sure.
Slack,
Sure.
and you can discuss it on Slack.
So yeah, hi everybody. My name is Kai Brünner. I work at the Bern University of Applied Sciences, and I report on work that was essentially done by two bachelor students of mine that used the stainless verifier in order to verify some properties of the Bitcoin S library. Just some quick words about what Bitcoin S is. That's a library to validate, serialize, deserialize Bitcoin transactions, and so on. Stainless is a verifier for a subset of Scala. So it's a subset of Scala. It doesn't support all of Scala. So in particular, that was the main difficulty in this work, to rewrite a part of Bitcoin S in order to be able to handle it with Stainless. And finally, and that is the main contribution, I think, of our work, is that we found two bugs in Bitcoin S, one of them fairly serious. So first of all, Bitcoin S, I mean, that's just some example code. You can generate private keys, you can generate public keys from that, and then you can generate a UTXO, so a transaction output, and then you could put together a transaction here, that transaction. Yeah, and then you can send it off to the Bitcoin network, for example. Wouldn't work with that particular transaction. So that's Bitcoin S. Stainless is a tool that allows you to annotate your code with specifications, so pre and post conditions. So this is a precondition. I require that n is greater than 0 in this factorial function, and this is the post condition. I want to prove that so whenever the input is greater than 0, then the output will also be greater than 0. And this is, of course, not true for this particular function. Maybe you can see why. So the integer, the Scala integer, is just a regular Scala integer, and it's, I think, 32 bits, a 32-bit integer. So that won't work, right? And Stainless tells us this. Stainless actually gives us a counter example. It tells us, you know, for n equals 17, your post condition does not hold, right? So this is very useful for a programmer. I mean, so this is just you know, you just run Stainless on it and it gives you a counter example if you're lucky. Now, Stainless only works on this subset of Scala, which is essentially algebraic data types, which are called case classes in Scala, and pure functions, so no side effects. But there are some things that it doesn't include. So for example, objects cannot inherit because objects are essentially just used as namespaces in pure Scala. Abstract type members are not supported. Inner classes in case objects are not supported. Lots of things in Scala are not supported in Stainless and in pure Scala, right? And that was the difficulty in this work. So just to give you some examples of what we had to do. So here's an object that inherits from some class, which is not supported. So we had to turn it into a case object, which is not a problem here because that can be represented as an algebraic data type. No problem here, no state. The second thing is abstract type members. So there's a class with an abstract type member that's supposed to be overwritten in the implementing classes, and that's not supported. So we just replace the abstract types by the concrete types, which is possible in this case because there's only one type that overrides the abstract type. And finally, there's another example. So Stainless has its own library of functions. So classes and functions. So for example, big integer, but the Stainless big integer is not the same thing as the Scala big integer. So for example, it doesn't support bitwise operations. So this code also is not supported because there's no bitwise operation supported in Stainless. But it turned out that this function was redundant anyway. So that's a bug that I will talk about shortly. And so we just removed it. So these are 3 examples of how we rewrote a fragment of Bitcoin as a small part of Bitcoin in order to verify our property. And here's our property. So there's a plus functions and it adds Satoshi amounts. And what we want to prove is that if I have 0, if the Satoshis that I'm going to add to the existing Satoshis are 0, then my Satoshi amount stays unchanged, right? So this is the post condition. And after all our rewriting, so I just showed 3 examples, but there are actually 10 kinds of rewritings that we had to do. We are now finally able to verify that with Stainless. So we're happy about that because if you receive 0 Satoshis, you wouldn't want your Bitcoin balance to change, right? But it's not particularly, so I don't view that as a particularly interesting contribution of our work. I think the more interesting contributions are the bugs we found. And the first bug is, well, so there's a check transaction function in Bitcoin as in it checks transactions. And for example, it's supposed to check that there's no double spending inside one transaction. And the check that the Stainless developers implement is actually too restrictive. So we changed, we removed the overly restrictive check and replaced it by the right check. So yeah, that was the first bug. It's not that interesting. But here's the more interesting bug. So what they do is they have the check result function that was the one that used the bitwise and it used the bitwise and in order to check whether some operation led to an overflow. But the problem is that the way the Java bitwise and works is it never actually checks for an overflow. So this function is useless. So it doesn't do anything. It doesn't actually check the result. So this I would say a grave bug that we found and that we removed. Now it turned out that the only places where the check result functions ever called are constructors in which the operands are checked anyway. So we checked and it's actually redundant. It's not only buggy, it's also redundant. So these are the 2 bugs we found. And the lessons that we learned from this sort of case study of using Stainless on real world code is that, you know, even verifying very simple properties requires significantly rewriting existing Scala code. And this is true. Well, this is not particularly surprising, but what was a bit surprising for us is that this is true even for purely functional code, right? So the part of Bitcoin S that we looked at doesn't have any vars, doesn't have any mutable state in it. And still we had to significantly rewrite it. So it's not really, yeah, we haven't really verified existing code. Really, we verified a re-implementation of it, right? That's more honest, let's say. But attempting to verify has been very useful for finding bugs. And that is actually what the Bitcoin S authors care much more about than successful verifications. Yeah. So thank you very much for your attention.
Yeah, thanks, Kai, for the nice talk. I have a last short question. You said that it was a lot of effort to port the code to be able to verify it. Do you have some? Can you give us some numbers or some idea of the effort it took you?
So in terms of lines of code, it's not that much. You can check it on the GitHub. Check it on GitHub. It's maybe 200 lines. It's not much. Now it took 2 bachelor students half a year. Let's say, you know, if that is so a lot of, actually it's not that much of an effort. It's just, yeah, maybe I shouldn't say it's a lot of effort. It's just not. The code is not the original code, right?
Okay.
So it's different from that. And it's not, you cannot say, I think you cannot say, look, we verified the original code because we haven't. We verified the transformed code, the rewritten code. So the effort, yeah, I don't wanna, you know, harp on this. It was a lot of effort. It's just, maybe compared to our expectations, right? So our expectation was, this is purely functional code, so we should be able to run Stainless on it right away, and that's just not true. Yeah.
Okay. Yeah. Thanks a lot, Kai. We are now at the end of the first session, and we will now split the participants into breakout rooms so that you have the possibility to chat a bit with each other, and then we meet here again, or we close the breakout rooms again in 10 minutes, which means 2:30 for the next session.
Yeah, I'm going to create 3 rooms for each of the speakers, and I'll try to have at least 1 speaker in each room. And if you have any desire or complaint if you want to change rooms, just say something on the Slack maybe. I'm not an expert with Zoom, so. Okay, I think we should start the new session. So the next talk would be by Giuliano Loza about formal verification of a stellar consensus protocol. Maybe Giuliano, you can start and share your screen just to check that it's working.
Yes. Let me
Right.
try that. Is this working?
Yeah, very much so.
Awesome. Oh, I have an issue here. Anyway, so can I start?
Yes, please do so. Sorry.
All right. So today I'm going to talk about the formal verification of the stellar consensus protocol using the IV methodology. So this is joint work with Mike Dodds at Delaware in Portland, Oregon. So what's interesting about this work is, I'll state it right now, is that it's an application of the IV methodology to a quite complex protocol, and it pushes the methodology a little outside of its usual bounds. That's what's most interesting about the work in my opinion. So that being said, so let me start. Somehow I cannot change slide. Here we go. Okay, so why the IV methodology and what is it? So in a nutshell, with IV, what we're trying to do is verify protocols using only decidable logics. And the point of doing this is to ensure that when we send verification conditions to the backend solver, Z3 in this case, Z3 will behave reliably and it will not diverge. It will say either yes, your verification condition is good, or no, and here is a counterexample. So the problem is that decidable logics are not very expressive, and so we need tricks to model our protocols in those decidable logics and reduce verification conditions to decidable ones. For this work, we're going to use a logic called EPR, which is a fragment of first-order logic. And what you can see on the screen now is a workflow, the workflow that we use to verify safety properties. So first, we model our system as a first-order transition system. We model the property to check as a state predicate, and then we give candidate invariants that are supposed to be inductive invariants that imply the property to check. Given those three things, IV's verification condition generator generates verification condition, which it passes to the fragment checker. At this point, the fragment checker checks whether the VCs are decidable or not. If they're not decidable, it just stops there, and it says it reports an error to the user, and it shows an explanation as to why it's not decidable. If they're decidable, then it passes them to Z3 verification condition. And so the key property here is that every query, every automated piece of automation reliably produces an informative output. There's no, in practice, divergence where the user doesn't know whether the verification condition is valid or not. And so this makes for a more productive proof environment. Now we also can verify liveness properties with Ivy, and this works by reducing verification of liveness to safety. So the workflow is similar, except that so we start with our transition system in first-order logic and a property expressed in LTL. Given those two, Ivy will automatically produce a new system and a new safety property, such that if we can prove that this new system is safe, it implies that the LTL property holds of the original system. So once we have the new transition system and the new safety property, then the workflow is exactly the same as for proving safety properties, obviously. We have to provide a candidate invariant, this time that talks not about the original system, but about the generated system. And then, so Ivy will check that the verification conditions are decidable and then pass the formulas to Z3. Okay, so one of the main hurdles in applying this to the Stellar consensus protocol was first modeling the protocol in first order logic, and in particular in EPR to get decidability. So here's an example of what this means using a much simpler protocol, Paxos, which is also a consensus protocol. So in Paxos, nodes vote, and if a majority of the node agree on something, then they all decide on that value. And so if we want to model this in EPR, we cannot use a cardinality definition of quorums because that's not part of EPR. But we know that the algorithm relies only on quorum intersections. What we do is we axiomatize the quorums, as you can see on the screen here. So we define 3 types of node, value, and quorum. A relation member, which expresses set membership. And then we just give an axiom that says that any 2 quorums have a member in common. And then we can define our protocol talking about those quorums. Now, for the Stellar consensus protocol, this step is much more difficult because so SCP, in fact, is a protocol a little bit similar to Paxos, where nodes vote, and if a quorum agrees, then they make a decision. But the key difference is that in Stellar, the system is permissionless. So anybody can join and leave the system. And so it must tolerate Sybil attacks. And so it cannot use threshold quorums like Paxos because we don't know how many nodes there are and it's been changed arbitrarily. So instead, in the Stellar consensus protocol, nodes declare trust relationships, or we also call them agreement requirements. Then the notion of quorum emerges in a distributed fashion from all those agreement requirements. But in short, a quorum of a node n is a set that satisfies the agreement requirements of the node n and of all the members of the quorum. So the notion of quorum is personal to a given node and depends on the configuration of other nodes. So this is called a federated Byzantine quorum system. So this is a little harder to analyze than the typical threshold quorums. And so our paper is mainly how to model this in first order logic and in EPR. So as with Paxos, where the key property was quorum intersection, here for SCP we have 3 key properties: quorum intersection, quorum availability, and the cascade theorem. And you can see the full EPR model here on the slide. So I don't expect you to read that, but just to show the size of it. And so it's a little tricky, and it's not very clear that it's sound. For Paxos, the quorum intersection is a pretty simple property, but here it was not clear that this model is sound. So what we did is we modeled these federated Byzantine quorum systems in Isabella Hall from basic principles without using axioms. And we proved that all those properties that we have here hold in the Isabella Hall model. Finally, you can see here that the last axiom, the cascade theorem, is an axiom schema. And so there we depart a little bit from the traditional IV methodology because this is in fact a second order theorem that we manually instantiate when needed. So having done that, we proceed with the usual IV methodology, and we observe that the proof of effort is actually pretty low once this is done. So we verified safety, meaning that 2 intact nodes never disagree, where intact is a particular set of nodes, a particular stellar. And we proved liveness, assuming a variant of eventual synchrony, and every intact node eventually decides. And so it took the specification is about 150 lines. The safety proof is very short, doesn't invariant, and the liveness proof was much more involved for technical reason, not because the liveness itself. About a month for work to do it.
Sorry, Julian. Yeah, sorry. Okay, all right. Sorry.
All right. Did I? Yeah, sorry if I ran over. Yes.
All right, so we're a bit short on time, so maybe I'm going to ask quickly the questions that are on the Slack channel. So 2 questions from Maria. Could you elaborate a bit on future work? And second question, can you relate your proofs to executable code for the protocol? So that's for Maria. And Joseph Guider is asking about some intuition on the abstraction that allows you to get a finite state system for the liveness proof. All right.
Right. Okay. So first question. Yeah. So future work. So one obvious one is that we produced a quite high-level model of and bringing that down to something more concrete, and maybe when implementation is an obvious next direction. But the IV methodology actually allows us to go down to an implementation and generate C++ code for this. So I think that kind of answers the first two questions. And then Joseph asked the abstraction that allows to get a finite system for the liveness proof. Yeah, so for the liveness proof, essentially we do it by contradiction. So we assume that there exists a ballot after which the system is synchronous, but yet one node doesn't decide. And in the protocol, the node is supposed to decide in the ballot following the first synchronous ballot. So we know that we can project the system on all ballots smaller than GST plus 1. And that's going to be our finite abstraction.
Okay, thank you very much for the answers, Giuliano. Without further ado, I think we should go to the next presentation by Joseph Guider. He will talk about formal specification and model checking of the Tendermint blockchain synchronization protocol. Yeah, Joseph, whenever you're ready, yeah, you've shared your screen, that's great.
I'll also unmute me. Yes, hi, I'm Joseph. So I'm going to give you a quick presentation of this work. So it's about formal specification and model checking. So in the paper and also a little bit in the long talk, we're going to talk a bit about our approach to specification, which also includes a structured way of writing English specifications. It's also in the paper, we found much more detailed discussions about the TLA model and the model checking results. And you'll also find some introduction to the Tendermint system. It's a proof of stake blockchain, and it has several protocols which are important. So in addition to consensus, there's also blockchain synchronization. And this is sort of what this work was mainly about. So Tendermint blockchain synchronization. So the main problem that you are solving here is that if a node was disconnected from the network for some time and missed some updates on the blockchain, the question is how to catch up to the latest state. And this is what this protocol was designed for. Because of this, the way the trust works in Tendermint, you need some initialization, which we call subjective initialization. So you need to know the first block, which gives you the root of trust. And then basically what the protocol is managing is to ask the question is which node to ask for which new block and to download this. So there's a lot of load balancing going on and a lot of understanding which peers can ask and which are responding and which ones are faulty. And of course, the problem is you should not trust anyone. So you get these blocks and you will have to check whether the blocks that you get are actually the ones that come from the blockchain, because it's a Byzantine system and peers can gain some money and have incentives to lie to you. So the blockchain synchronization protocol addresses two problems. So problem one is how can I check that the block is actually from the chain? This is what we call to verify a block. And the second problem is which blocks to download from where. And our specification and our models captures both problems, but since we're a little bit short on time, I will focus in this talk on the blockchain verification. So Tendermint blockchain is a proof of stake system, which is basically a new implementation, modern implementation of classic Byzantine fault tolerant consensus algorithms, particularly the one by Dwork, Lynch, and Stockmeyer. And as a result, you repeatedly execute consensus for each of the blocks. And consensus is executed by nodes that we call validators. So they're also stored in the block. And the validators here in running consensus not only decide on the application and the data, they also decide on who is going to decide on the next block. So in some sense, the group membership is dynamic and it's decided by the consensus. So in this example here, next validators are, of course, the validators for the second block. Now, as I said, it's subjective initialization. Assuming I have block 1 and I have downloaded block 2 and block 3, I have to figure out whether I can trust block 2. And the point to do is that in the third block, we store actually the commit. So these are the signed messages that say that these nodes here who have votes want to decide on that block. And since, of course, they sign the hash of the previous block, and if there are sufficiently many, and in this case, we need signatures from more than 2/3. So if all the signatures are there, and if the hashes are there, then we can trust block 2. So there are several consistency checks that we have to do, like this one, and we want to capture them in the protocol and in the implementation and in the specification. So as I said, in our approach, we sort of, as a basic document of knowledge is the English specification. So this is not like prose English, it's actually quite structured. We require that properties and specifications have a clear meaning in temporal logic, because these English specifications are a basis for both the implementation and the formal work that we are going to do in TLA+. So we also have TLA+ specifications for the protocols. I just give you here a small part of it. And this here is our specification of the chain. So it's an abstraction, of course, of what the property that we define of the chain. I mean, there are certain things we are interested also in model checking. We cannot treat hashes and digital signatures explicit, but we have certain abstractions here in place that model the behaviors of the blocks and the relationship of a block that we receive to the block that is actually from the chain. So it's quite intricate. I'm not want to go into too much detail, but the main point is that we believe, so there are certain projects that are happy once they finished writing TLA+ specifications, because it's already there, often problems show up. But we believe it's actually worthwhile to dive deeper and do some model checking on them. So this means first we write more properties than the one that actually sort of come directly from information from the engineers. And we use TLC, which is the standard model checker, and run it on AWS. And we also at Informal System maintain our own TLA+ model checker, led by Igor, who is also in the room, I guess. And we use these two model checkers to check the properties. So we started with some initial models and with some initial specifications, and in short, all safety and liveness properties are violated. Of course, there are reasons for that. One point is that sometimes one is naive when we write down specifications, what we expect that the thing is doing, especially in a fault-tolerant asynchronous context. So we had to refine the properties, and we get a better understanding of actually these properties that the protocol is maintaining now. Also, in the initial formalization, there were some block verification steps missing that are actually in the implementation, but that were somehow not captured in the documentation that we found. So we had to refine the description of the protocol in TLA+. And also the blockchain model, which is sort of the reference model against which we have to compare and have to write a lot of specification, was too abstract to verification. So, but in the course of this model checking work, we were able to fix all these issues. So the important thing, the lessons that we learned here, is that it's actually very useful to spend time even in model checking, and because we actually found the properties that the protocol is verifying. So model checkers give you counterexamples. We look at them together with engineers, sometimes just among our researchers, and we figure out that they were too optimistic, and we refine what's going on. Also, that in the similar things that we had yesterday in the talk, where timing constraints between two blockchains showed up here, similarly timing constraints showed up in the protocol, and we were able to formalize them. So the important point is we should do verification as soon as possible. Don't do it after the fact. The earlier you can do something on the specifications, you will find things and better understand the protocol and the things it guarantees. And the second lesson is that you should try whatever invariants that come to your mind that might sound useful to you, even if they're not specified or not given by the designers of the protocols from the beginning. Even if they're trivial, because they will help you to debug things and get more deeper insight. And of course, what we also learned is that TLL+ actually is a very good communication tool. So all our software engineers get more and more fluent in TLL+. They start to write specifications themselves. Of course, they are very, very fluent in reading them, so they can discuss protocols and details there. So this is very, very helpful. And yeah, and with model checkers we can do more than just specifications. So here you find the links to our TLL+ specifications. They're also in the long version of the talk and in the paper. And to conclude, I will just show you the team who did this work. So from left to right, this is Sean, our CTO, Ethan, our CEO, then it's Igor, Sharko, and Elena, researchers, and to the right is Anka, she's also a software engineer, and I'm the guy second to the right. Thanks.
Thank you very much, Joseph. Maybe a quick question as we are a bit low on time. So in your work, you have been collaborated with software engineers that may not have a deep background in formal methods. Do you have any lessons that you can share with us about how to collaborate smoothly with engineers that may not be very familiar with model checking and other
yeah, I mean, so they are perhaps not familiar with model checking, but they understand programming very well and they understand what they write. So they are very quickly took up TLA+ and are able to write things. Or sometimes the models that they write in a very imperative style, and most likely they're not the most efficient one for model checking, but they give a good basis and we can then work on them. The other thing is that, of course, what I consider is the biggest challenge for them is temporal logic. So LTL, especially liveness properties, is something which is not very intuitive, and there is, I think, still some work to be done to get all our knowledge about temporal logic in a broader computer science audience.
Okay, thank you for this short answer, and thanks for making it short. So now we can move on to the last talk before the breakout. So that will be by Florian Kamuller. Sorry about the mispronunciation, about proving interblockchain protocols with the Isabelle infrastructure framework. So Florian, yes, you can start. Okay.
Can you see my screen?
We can hear you. We can see your screen. At least I can.
That's great.
So whenever you're ready.
I'm ready. Okay, so thank you very much. So this is my presentation on interblockchain protocols with the Isabelle infrastructure framework. And it's joined, so I'm Florian Kamuller, and that's joint work with my colleague Uwe Nestmann from TU Berlin. I'm at Middlesex University, but also affiliated with TU Berlin. So here's just the overview. So it's a short version of the long talk, which is recorded already. So the interblockchain protocols define and control exchanges between different blockchains. That's the main, I think that's the main difference here, which needs to be pronounced, that, we're looking at, it could be all kinds of, it's a heterogeneous set of different blockchains that we're looking at. And what we've been doing is that we use Isabelle basically, or we use the Isabelle infrastructure framework, which is an extension, a package, if you want, of Isabelle to reason about IBC, which is interblockchain protocols. The Isabelle infrastructure framework is focusing on supporting proofs of systems, which might have some sort of physical aspect and policies, and it offers a sort of state transition-based view of system semantics in order to support reasoning about the specifications of systems. And so the incentive of this work was to, well, first of all, to show that the framework actually works and makes sense by applying it to formalizing the IBC. But also, and that's probably the even more important, is to support IBC by basically helping to clarify certain incentives of IBC and looking at security things, security questions, security properties. And one property which out of this first formal specification in the Isabel infrastructure framework came out, and which is part of this paper, is what we've named global consistency, which also somehow could be read informally as saying the IBC is really a blockchain of blockchains. So the whole development, including the relevant part of the Isabel infrastructure framework, you can have a look at my GitHub. Right, so, oops. Here's just a slide kind of giving a very short idea of what IBC are. So as I said before, IBC allows communication between different blockchains. And one of the central parts in order to understand the concept is this idea of a relayer process, which you can see in this picture, which I've just cut out of the IBC documentation. So the relayer is a process that stands between two different blockchains. And it's also coined the logical core of IBC. It's off-chain, which means it's not part of any of the blockchains. It sort of stands aside, connects the different blockchains, and is responsible for relaying IBC data packets between the blockchains. The main actions that the relayer can do are scanning the states of all the involved blockchains and then submitting data. So these are the two actions we've been looking at. When we formalize this, and here's just a snapshot and overview of the Isabel infrastructure framework. So as I said, it's basically an extension of the interactive theorem prover Isabel, and all the black boxes on the bottom are basically very generic extensions of Isabel and consolidate the Isabel infrastructure framework. And on the very top, the blue box is then the adaptation of that more or less generic infrastructure formalization to this particular application, the IBC, including some extensions that had to be added, because here we actually have to look at sets of infrastructures that communicate with each other. We had to identify as sort of a special infrastructure process, the relayer process. But the lower boxes, like the refinement, the attack trees, and the crypto structures in CTL, are very, as I said, generic so-called conservative extensions of Isabel. That means they're not axiomatic or anything. So all the properties are basically derived from first principles, and hold the notions of state transition systems done using axiomatic type classes. It's very generic and allows instantiating all the machinery, like basically the temporal logic machinery, the attack tree formalism, the idea of building refinements of system models, to instantiate those to, in this case, to the application of infrastructures. So here's already the main result. This global consistency preservation theorem, which I consider as a proof of concept of this formalization experiment. So it kind of allows to express consistent data representation across different blockchains. And someone has been asking on the Slack, how does it really read? So I make an effort to explain it intuitively. I think really this global consistency property, as it is printed down there, this is the Isabel code, basically says for any two blockchains, I and I prime, which are part of that set of blockchains which consists of that overall IBC system, they need to be consistent in what information they have about any data item. So basically, you could also say this global consistency property is what I initially said, saying that an IBC system is actually a blockchain of blockchains. So it basically realizes the consistency between all the different blockchains. And the theorem we could prove on this definition of global consistency in Isabel is basically this theorem down there, which basically says that our semantics, which is this arrow with the I, which is the infrastructure state transition, or in this case, the blockchain set or IBC state transition, says if we have a state of our IBC system, IL of being globally consistent, and IL goes over in one step to IL prime, which is the next state of the system, then the next state will also be consistent. So in conclusion or summary, we provide an abstract model of IBC using the infrastructure framework, and we could express and prove the global consistency preservation property, which basically represents this idea that IBC is a blockchain of blockchains. And well, our most important goal is really to take this a bit further from like a first academic experiment and establish that some sort of link to industry, talk to companies who work on IBC and see what could be useful. I mean, what could be useful next steps in order to support the verification of their designs and implementations. Thank you.
Thank you very much, Florian. So we have a question from James. His question is, can you provide some intuition on relayer protocol? As a smart contract A in blockchain A, can I imagine consuming the contract state B of another chain B as a two-phase commit, or does it work differently? It's on Slack.
Oh yeah, I've seen the question now. Yeah, I don't know. I don't really know. Yeah, I think the intuition sounds pretty good. I mean, in some sense, these protocols are very, very abstract. So consuming the contract state B, I don't quite know what consuming means, but I mean, so the basic action of these protocols on a very high level is that the relayer just checks one blockchain and sees what is there exactly. So what is their consensus on what should be the next step, and then actually conveying that state over to, by doing a submit action, over to another blockchain. I don't know whether that really answers that question, but I mean, maybe we can continue this on Slack for a bit.
Yeah, a small question since we're a bit out of time. Would it make sense to use the same the infrastructure framework for proving properties about consensus algorithms? I mean, my impression is that the interblockchain protocol is not really a consensus algorithm, but maybe I might be wrong in that. But do you have any comments?
Do you say it's not consensus driven?
I'm not super familiar, so maybe it's a super naive question, but basically, I guess my question is, will it make sense to use the same methodology for, say, consensus algorithms?
I don't understand that word, consensus.
Consensus algorithms, like regular, like BFT. I mean, my question is about the Isabelle infrastructure framework and how expressive it is and how.
In terms of consensus, is that the question?
Yes. Does it make sense to use the Isabelle infrastructure framework for other blockchain problems? For example, the consensus algorithm, proving properties of consensus algorithms.
Yeah. So I mean, I'm not quite sure I understand the question correctly, but okay. If it's about the consensus part, because I'm also in the consensus session, and I didn't say much about the consensus, so we kind of use a very, very abstract way of representing consensus without any semantics in the formalization. But we actually, the Isabelle infrastructure framework enables to reason about specific consensus algorithms. So, and there's one example and is already done in the formalization where, a very simple way of consensus is implemented sort of later on using locales, so which allows you to do some sort of local definition and offers like one instantiation for this very abstract consensus thing. I don't know whether that answers the question, but
I think it does. Yeah.
Okay, good.
Thank you very much.
Thank you.
I suggest we move now to breakout rooms for the next 10 minutes or so, and then we come back at 7:15 Los Angeles time.
Yeah, we create three breakout rooms, and in every room there will be one of the speakers, so you can feel free to ask the speaker questions. Okay, I will start the breakout rooms now.
Okay, let's wait a bit until we start the last session. So Jacob, I think you can, you need to wait until we upgrade you as a co-host so you can share your slides maybe. So wait a second, it's coming, sorry.
Okay, can you see this and hear me?
Yes, we can hear you and we can see your screen, and I think it's about time to start, so feel free to start your, so now we have 5 lightning talks, so the presentation are a little bit shorter still, 3 minutes and 3 minutes of Q&A, so thank you, Jacob.
Yep, so in this lightning talk, I'll talk about our work on verifying, testing, and running smart contracts in Concert. So Concert is a COG framework for reasoning about smart contracts that we have previously developed and published. And in this work, we extend Concert in 3 ways. We implement extraction to liquidity and midlang so that you can take contracts that are written in Concert and get contracts in those languages. We verify another complex smart contract for boardroom voting. And then we add a property-based testing to Concert using the quick check testing framework, which is similar to the quick check framework that exists for Haskell. So to demonstrate extraction, there is here a counter contract that is written in COG in the Concert framework. And we use here refinement types, which is a feature that is not typically available in smart contract languages. So with refinement types, we define the set of positive numbers to be an integer and a proof that the integer is greater than 0. Now we can define functions on positive numbers, like we define an int counter function here that also use refinement types. So not only does it return a new value, it also returns a proof that the new value is greater than the old value. And the programmer will be asked to prove this in normal COG style, which we have omitted here. But now when we want to use this function, we also need to provide proof that the input we are passing it is also greater than 0. So to do that, we just check if that's the case. If that is the case, then we get some witness h, and this h we can pass to this function here. So here we pass I, which is the integer itself, and then h, which is this proof that I is greater than 0. And this extracts to these 2 extractions. So we have a liquidity and midlang extraction here. They follow the structure of the original program, except we have gotten rid of these proofs that were there before. So previously we had I and H. Now we have just I, because we know that these proofs do not contribute anything to the result. And this means that we can use refinement types in, for instance, COG, and then we can still get an efficient liquidity or midlang extraction out of it. So our next contribution was this boardroom voting contract that allows small-scale anonymous e-voting. So this is based on previous work. And in this contract, a set of parties submit anonymous votes to the contract. So the votes are public, but you cannot. But the public votes does not reveal what is the actual private vote. And at the end, the contract can then, from these public votes, compute a public tally. And we prove then that the computed result will be correct. So that looks something like this in COG. So we say that if the contract has not tallied yet, well, then the result is still going to be none. While if it has tallied, well, now the result is something, and the result is going to be the actual sum of the secret votes that correspond to the public votes that were sent to the contract. So either for or against this particular issue that was being voted on. And our final contribution is to integrate quick check within this Concert framework. So we do this in a semi-automatic way where the programmer is still responsible for writing something. So he must come up with the properties that he wants to test, of course, but also he has to tell the framework which kinds of messages can be sent to the smart contract. But after this, the contract can automatically generate traces, and we can then use quick check to check if for a bunch of traces if this property actually holds on these traces or not, and then you can get a counter example saying that there is a possibility of your property not holding. So I think that concludes my time. There are more details in the video and in the extended abstract, and the code is also available on GitHub. Thank you.
Thank you very much, Jacob. Maybe a very quick question, maybe for the audience. Could you say a few words about Midlang?
Right. So Midlang is the language that that's running on the Concordium blockchain, which is similar to Elm. So it's a very straight or very uniform functional language. So there were some differences between Midlang and Elm. So you can see here in these extractions, there are actually some minor differences. So syntactically, of course, there's a difference, but also you can see things like in liquidity, we do not have this SIG type that ends up being in Midlang, and that's because liquidity does not support variant types with just a single constructor, while in Midlang there are no restrictions like this. So it's slightly more uniform, and we don't have to do these kinds of remappings that we're doing here.
Okay, thank you very much for this quick answers, and I encourage everyone to have a look at the longer version of the talk and as well as the resources online.
Okay, yeah, thanks again, Jakob, and we can straight start with our next talk, which is given by James Chang, and it's a summary of Bitcoin TraceNet formal contract verification at signing time. Chang, can you? Yeah, perfect. Can you unmute?
Yes, thank you very much. Perfect.
Okay, then just go ahead and start your talk.
Got it. Can you guys see the full screen, or am I still on the browser view?
We can see the full screen, but you didn't start the presentation yet.
Okay, there we go. Is my slide on the view, or?
No, we are still looking at the not presentation mode.
At the browser, yeah.
At the browser. Okay. Not sure why it's not. I'm stuck on
Probably you shared the browser.
Yeah.
App.
Yep.
But you can also go with this way if you want. So.
Yeah, I'll just go with this. I'll just go with this. Okay. So thanks for having me. My name is James. I'm a PhD at the DTU. And I'll be providing introduction to Bitcoin TraceNet, which allows us to do contract verification at signing or runtime. So on the first slide, let me just collapse real quick. On the first slide, I show two ways of implementing a Bitcoin contract. On one hand, we can use a specification language like BitML, and BitML is a process algebra which compiles down to Bitcoin transactions. So that allows the user to focus on the contract logic. The advantage is that this process algebra is executable, so you can verify certain properties at the symbolic level without having to deal with the transaction level issues. The trade-off there is that you no longer have transaction control. So in some cases, you may have reduced privacy because of the transaction graph. It leaks certain heuristics. Sometimes it leads to higher execution cost. So on the other hand, you can implement a contract directly at the Bitcoin transaction level. And this has disadvantages. So for one, you're reasoning about Bitcoin script, you're reasoning about actor knowledges in different contract states, and you have a transaction graph you have to reason about. The advantage is, of course, that you have full control of the transaction graph. So you can optimize for privacy, or in some cases, you can optimize for reduced on-chain transaction or execution cost. So verification on the transaction level has been a little tricky thus far. It's mostly manual proofs or manual models, and TraceNet aims to provide the ability to perform automatable generation of models that can be model checked in runtime. And because we are working on the transaction level, we can provide a relatively accurate blockchain model, which I'll show in a second. So the Bitcoin TraceNet contract state consists of the following tuple. We have the internal actor knowledge, the external actor knowledge, and the blockchain's contract state. And the internal actor is the verifying actor. The external actor are models all other actors participating in the contract as one colluding actor. All actors have access to a set of public functions with which they can expand their knowledge, $VL style. And we have 5 different types of transitions. The most obvious one is the direct message with the counterparty, which updates the knowledge of the recipient. There is some kind of information is being exchanged, be that signatures or a transaction, public keys, and so on and so forth. Then we have the transaction broadcast. That is when a signed transaction is broadcast to the network. That may update the knowledge of the observer if it contains information previously unknown to the observer. We have confirmation. That's when the transaction is amended to the blockchain. There can be delays, time delays, either enforced by a contract or a delay between broadcast and confirmation. And we can also model blockchain reorganizations. So the counterparty or the external party can perform a 51% attack up to a certain depth and reorganize the contract transactions in this new fork. And that's really nice. So we can define certain parameters for which a contract safety property must hold as well, even in the presence of reorganizations. So what do we do in TraceNet? We start with a initial state of the actor knowledges. And one can think of this as either a state generated by the contract client implementation or the contract specification, right? It specifies what public keys are being generated by whom, what are the transaction templates, so unsigned transactions. And what we then do is we generate a executable symbolic model from the initial actor state. And so this is basically extended PetriNet model, which includes the time lock semantics from Bitcoin. So for example, older time locks are modeled here. There are earliest fire times for both older time locks and after time locks, both in block height. So that's the TraceNet model. And given an initial state of the TraceNet model, we can now expand or unfold the reachability graph, along which we can then perform model checking for the properties or trace properties of interest. In particular, we're interested in the traces where the verifying actor can reach a safe terminal state despite any adversarial actions by the external party. So that's nice. So in summary, we are providing a formalism for verification for contracts which are implemented at the transaction level in Bitcoin. This has certain advantages and disadvantages. The advantages include more control of the transactions, optimized for privacy or reduced execution cost. And one of the neat applications we think that is useful is this allows us to perform or enforce safety policies, universal safety policies for contracts being executed at runtime. And so that's the summary. The full paper is on archive, and there is an extended video on Fmbc. So thank you for having me. I'm happy to answer any questions.
Thanks, James, for this nice talk, right in time. We have time for one short questions, and I would be interested if you could give us an example of a property you would like to verify with your approach. So
yes.
Do you have already something in mind, or?
Yes. So I have one slide in the appendix which I can show to illustrate this. So in particular, there are certain contracts which we denote as trustless. They can be executed in a trustless fashion. And the intuition there is, I want to be able to participate in this contract with you, and I want to be able to recover my funds despite any adversarial action that you may do. You may disappear, or you may erase my transactions on chain. And so one way to formalize this here is this following slide here. So we have some state Z, or LZ actually, but let's say we have one initial state here, and there is a trace which is fireable by the internal verifying actor, which reaches a safe terminal state. And there may be transitions or intermediary states which the external actor can erase, as in here or here, but that's fine as long as the resulting state also has a terminating trace, which I, as the internal actor, can fire, right? So this is a bit of a recursive definition, but this guarantees me that no matter what happens, starting from here, I will reach either this state, or this state. And if all these states are safe terminal states, this is a safe particle for me to participate in.
Okay. Thanks, James, for your talk.
Thanks for having me.
Okay, the next talk will be by Benjamin Vass. Benjamin, Diego, you need to upgrade Benjamin as a co-host so he can share his slides. So Benjamin's talk would be about high assurance field inversion for pairing-friendly primes. And Benjamin, I should be able to share your screen. I'm not hearing you. Yes, we can hear you.
Can you hear me?
Yep, and we can see your screen. At least I can. So please go ahead and start your talk whenever you're ready. Thank you.
Thank you. Yeah, so welcome to my talk on high assurance modular inversion using field cryptography. So I apologize if I go offline. My connection is really bad, but yeah, so this I will present our work joined with Bas Phillips and Diego on implementing verified inversion. So first of all, we use this called cryptography. So I'll briefly what that is. So that is a library for sizing finite field, and the constant time, which is necessary for security against side-channel attacks. And the way you use this, you write some high-level coding, which is compiled Fmbc. And the thing is that this is a trick in prime and to your prime processor. So the language you can write is a bit, but not oops. So we had to fix that. The inversion algorithm is of Yang, and is a iteration of the step method you see, and this is constant, which again is necessary. We stated this algorithm in a fiat-friendly way, in the way that we remove some that were used to implement for multi-level integers and arithmetic shifting. So these were functionalities that are already in fiat, and we use together with the analysis already in fiat to implement this division step. Correct. So as I mentioned earlier, to generate loops, so we had to actually write this loop around the generated division. Good. So, and also as you see here, we only prove the function correction, not the actual algorithms. At the moment, not verified that when iterated actually computes the inverse. But here's some benchmarks. The first our works, so we get approximately 80 cycles, and compared to a handwritten, hand implemented very about a double slowdown. So we see that as reasonable where when you need the implementation to be verified. So just quickly for future work. So as I mentioned, the algorithm is not proven correctly at all the steps, and of course we wish to actually prove the algorithm correct, but this requires some more libraries. And we would also like to be able to actually generate the entire algorithm without having to write this loop yourself. And then long term, we would like to actually be able to generate some complex things such as elliptic curve operations and pairing algorithms. So I think that was time. If I recall correctly.
Yeah.
So thank you, and I'll take the chance.
Okay. Thank you very much, Benjamin. I'm sorry, I'm gonna, maybe just to improve the quality of the connection, I'm gonna stop your video. Maybe it will improve things. I think from my side, at least, it was not always easy to follow.
Yeah.
So, yeah, thank you. So maybe I'm gonna stop my video as well. So a quick question is like, could you say a few words about what is lacking in fiat crypto? So as I understood, your work is about to filling one of the holes of fiat crypto, but could you elaborate a bit and say very broadly what fiat crypto is missing to be fully complete, if that makes sense?
Yeah, so for example, it misses this inversion, right? So to actually implement all finite field operations, so which is the gap that we're trying to fill here, and working with it is it's not too well documented, but it's once you get into it, it's fairly easy to work with, and also quite extensible. So for example, we made this division step, but I don't see why you couldn't implement more complex algorithms using it. I don't know if this answers your question.
Yeah, a little bit. Well, thank you. Maybe we're a bit late, so maybe we're gonna go to the next talk. Thank you again, Benjamin.
Thank you.
Sorry, I didn't see I was muted. Let's go on with the next talk, which is about Albert, an intermediate smart contract language for Tezos, presented by Julian Tesson. Tesson, right?
Yeah. Yeah. Can you hear me?
Yeah, we can hear you well.
Yeah.
Or at least
and
I
you
can.
have my screen. It's okay.
You can see the screen as well. Yeah.
Okay, great.
Okay,
hi,
just go on.
Julien Tesson. Yeah, thank you. Julien Tesson from Nomadic Lab, a researcher here. And with a colleague of mine, we are designing an intermediate language for Tezos smart contracts, which is named Albert, the intermediate language. So we are aiming to compile toward Michelson, the language of the smart contract interpreter of the Tezos blockchain, which is a stack-based language. And I will skip all the detail here, but the thing is, targeting stack is not always easy. And all the high-level languages that I want to target Michelson will have to abstract this stack. And so we thought that the main point was to abstract the stack with variables so that they don't have to do that each time for each compiler. And we still keep track of resources because on the stack, when you use a value, it will be consumed. So we keep this in the intermediate language. Using a linear type system, we ensure that if each time we use a variable, it will be consumed and you cannot use it anymore. And we added a few more abstraction, like using record or NRA variant instead of OR type and pairs. And we also added non-recursive functions to help with building libraries. The global architecture of this has been written in OTT, which help us to specify the language, like its semantics rules, typing rule, and grammar. And we can extract parser and also inductive defined in Coq that represent the typing and semantic rules. And that's nice, but the drawback is that this is generated Coq code that is not always very readable. But the thing is, it's nice to have this for first prototype. And we write the typer and the compiler in the Coq proof assistant so that we can certify the correctness of the compilation later. So this is a work in progress. We have this formal definition of the language in a modular form with OTT, and a type checker and a compiler, which are right now more a proof of concept. There are some efficiency issues, but still we have a first version of the compiler. And what we want to do next with this, we want to design a OR logic to reason at this level of the language that would be probably much easier than to reason on the stack. And we want to have annotation in the language to control the translation toward Michelson, so that our program written in Albert can interact with other Michelson programs. And on the compiler side, we want to prove the correctness of the compiler, of course, and to be able to plug some optimizers and provide and have a certified checker that will check that the optimization provided by this optimizer are correct. And also a future work is to have a decompiler, hopefully a certified decompiler, which would allow us to ensure that we didn't miss any functionality of Michelson, that each thing that you can write it in Michelson, you can also have it in Albert. And I think that's it for my short presentation.
Okay, thank you very much, Julian, for this overview of Albert. You already mentioned it in your last slide. So you did not yet verify compiler correctness. Did you start or try to verify this already, or is it just a long-term goal?
It's I would say mid-term goal. We plan. Our first plan was to have this this year, and unfortunately we are late on schedule for obvious reason. And and so no, right now we don't have any proof, but we are confident that we can have. Well, I should not say that. We hope to have them next year.
Okay. Mm-hmm. Yeah. Then I think there are no other questions in the chat, or if there are, then people can ask in the chat and you can answer there for further questions. So thanks again, Julian, for the nice overview. And yeah, Bruno, you can.
So the last talk of a session and of the workshop will be by Luis Horta about YLSON. So Luis, we can hear you.
Yes, let me just share my screen, yeah.
Yep.
In a second.
Feel free to start whenever you're ready.
Okay, can you see my screen?
Yep.
Yep. Okay, so thanks for having me. My name is Luis Horta, and I'm going to present you our work called Wilson, Proving Your Michelson Smart Contracts in Y3. First, let me show you some of the motivation that led us to Wilson. We wanted to be able to provide both proofs of correctness and safety for Michelson smart contracts, and we wanted to automate the proofs as much as possible, as well as minimize the user interaction with the underlying proof tool, namely Y3. Additionally, we wanted to work at a Michelson level. This figure represents the architecture of our platform. We start with the Michelson written contract, which is then parsed, and the Y3 API alongside the axiomatic semantics produces a YML contract, which can then be proved inside the Y3 framework. As an example of the translation mechanism, we have this Michelson contract that simply adds a natural number given in the parameter to the one in the storage. Below this, we can see the generated YML code. Moving on to a more concrete case study, we present you this contract, which simply calculates the factorial of a given natural number. This example served as a test bed for our axiomatic semantics, and therefore it was manually translated, because our main purpose at this stage was to capture what our semantics could and could not do, rather than the automation of the translation mechanism. We are currently working on improving this mechanism so that it could split crucial portions of the Michelson contract into separate functions in order to facilitate their proof. So let's focus on the loop section of this contract. The first precondition assures us that the value stored at the top of the input stack is in fact the factorial up to the previous iterations. The last postcondition ensures that the value stored at the top of the result stack is the value of the factorial up to the current iteration. The operation fact that we can see here in this specification is the specification of the factorial definition from the Y3 standard library. Here's a picture of that proof session. This generated over 2,800 verification conditions, which were proved by Z3 and Altergo. To summarize, we successfully proved the first case studies of Michelson smart contracts using an auto-active verification framework. We found that algebraic data types are very hard for SMTs to work with, but we think that by going further in our shallow embedding, we can improve proof automation. As future work, we intend to develop a suitable specification language for Michelson so that we can embed specification directly in the smart contract. Additionally, we intend to prove that our axiomatic semantics abides by Michelson operational semantics, and we already have an operational semantics for Michelson in Y3, which we intend to use as target for this proof. This concludes my presentation. Thank you for your kind attention and questions. For more information, let me just add that the papers on the archive and the longer talk has more information.
Yeah, thank you very much, Luis, for this 3-minute talk, right on time. Could you elaborate? João, one of your co-authors, said that there was some links in the paper you presented yesterday and your work. Could you elaborate a bit on that, please?
Come again, sorry, I had a loss of connection.
Sorry. Yeah. Could you elaborate on the links, on the link between your work, Wilson, and the work presented yesterday by João?
By one of my co-authors, yeah. Currently, their goal was to prove that the semantics of Tesla abide by Michelson semantics, and by using the semantics that we have for Michelson inside Y3, implement a semantics for Tesla inside Y3 as well, and then prove their equivalence. I don't know if that answers your question or not.
Yeah, and another question is, are you familiar with the works with the Archetype project, and how does it relate with?
Yeah, I was familiar with the previous works of Archetype, but now that I saw, like yesterday, that they released a version like a week or two ago from Archetype 1.0. But I'm not familiar with the newer version. The previous one, I know that they had a specific language, and then they would use Y3 to prove their work, but they were not working directly at the Michelson level. I cannot say that I'm familiar with the newer version that they sent out, but I know of its existence. But I'm sure to
I think
research
you're
a
right
little.
that yeah, they don't target Michelson. I think they target higher level language, but that,
yes.
Yeah, maybe we will target Albert at some point.
Yes.
Presented, so yeah. Okay, well, I didn't see any question on the Slack, so I guess maybe we can end the session for now before going to the breakout rooms, and maybe Diego, you're gonna say a few words of.
Okay, thanks for having me.
Thanks again, Luis.
Yeah, thanks again to all the speakers. We had nice talks in these 2 days, and sorry again for the interruption yesterday. Also for us, it was the first online or purely online hold meeting, and we did our best, but not best enough, not good enough. But today it was better, and thanks a lot. Again to all the speakers, and we welcome ongoing discussions on Slack. So if during CAF you have other questions, just post them in Slack, and maybe we can keep the discussion going. Also, there is a session about blockchains going on Wednesday at CAF. So maybe could be interested for one or the other here in the audience also to participate in this session, to look at what CAF is doing in this, or the CAF authors are doing in this area. And yeah, we are also, so we got really high quality submissions this year again, and therefore we plan to do a version of Fmbc also in next year, in 2021. Hopefully, this will be again a physical event. Yeah, fingers crossed. And we would be happy to see many of you there and meet you in person then. We still did not decide where it will take place, but just maybe have a look at Twitter or at our website, then we will keep the information there. And finally, a few words on the proceedings. So please be sure for all the authors that you uploaded the last version on EasyChair. We will have a final look at them, and if everything is okay, we will basically distribute the invitation from OS6, where you can then upload the LaTeX source files, and then they will be published there. And finally, if you are interested in the details of the talks today, then just have a look at the YouTube videos. So we have 10 minutes to go until CAF starts. So we will start another breakout session now. I think we split into 5 groups for every and put one speaker in every slot. And maybe if there are too few, then we will move them. There's people leaving. Yeah, but let's try anyway. Okay, so enjoy your last breakout session.
can you stop the